I'm going to talk about these dynamics of confinement, and I'm going to first talk about charge transport in response to external fields in simple and polymer electrolytes, just because this is what relates to Sam Edwards. And then the second part, I'm going to talk about the things I'm very excited or I'm doing now, which is when you have actually surface-induced charge transport due to patches of charges or some activity, chemical activity, or charge distribution along nanoparticles. So, they do have some relation to the analysis that he actually did a beautiful talk in iotronics, where he introduced these concepts of trying to mimic the brain functions, and all of these very complex functions they have, like nonlinear electric responses and ion pumping. So if you think of it, what I'm trying to do is like make patches of charges and some activity, and then see how they generate some flow of transfer of things. So this his talk in the iotronics. But I have to start with polymers, which is what it joins to me to Sam. We was his student, and I was doing a work in polymer blends, and I over the years continue some problems in polymer blends, and this is a case of one where you have a dense system of polymers, but they have very few charges, the polymers. And these are called ionomers or polymer electrolytes. So in the figure, I didn't put the rest of the chain, which is the purple, the pink, but you can see that they form very strong clusters. And this is because this law is in a low organic, in a low dielectric constant media. And so the parameters, the parameters that one should look in these systems. Let me see, what is the pointer? Okay. It's you have Coulomb interactions, but in these systems, what is dominated is this length scale, which is called the Jerome length. And that's equal to, the charge square over 4 pi. You have to rescale by the electric constant of the medium, and there is the radius of the two particles that come in contact, because this LB, when you divide over this mean distance between them, this is what determines how strong they bind in that medium, opposite charges. And so if you look at this value gamma, it's of the order of 10 or 20, means you need 20 or 10 kTs to separate charges when you are in organic solvents. And molten systems like Nafion or PO, these numbers can be very large. So they are very strongly correlated systems, if you think of it. Some people call this T star the inverse of this gamma. And so in the systems in these polymers of the order of 0.1. And so this is because we talk about multi-components. I like to also show this example. If you have these systems, the charges are random when you make them. So they are really a multi-component systems. So if you just take two components, if the molecular weight is, say, 50 or 20, you have 10 to the 20 different chains. So even if the mean concentration distribution has some number of them 0.5, they have completely different sequences. So they're a very component system, and they don't seem to precipitate, but they form these clusters that are percolated. And so they are strongly correlated. If the LB is 0, or they have no charge, then they are not long-range correlated. But then when you increase the charge, they become very long-range structures. When you put a field, they change. So these systems respond to the field, and the size of the clusters depend on the ratio of the anion to the cation that you can put. So if you want to make them for applications, like how do you choose the bulk charges on the polymer versus the ones of the coions that you put in the structure? So that's the application part. So they have the mechanisms of transport of charge here of the ions is hopping or vehicular, right? So these are well-known mechanisms. When you put electric field, if you have a low coupling gamma between the clustering, then they actually hop, and then if not, you have vehicular, which is distort destruction. So this is, the message is that, in both cases, you are going to find nonlinear response systems when you go to strong fields. And here is the nonlinear part where you have where everything, the mobilities depend on that ratio you have, either in the strong electrostatics of vehicular versus hopping. Of course, everybody wants to have the hopping because you can see that there is an order of magnitude different, the mobilities that you have. So this is just a summary of this part. Another part that I haven't still talking about what I did with Airbus, but anyway, the other part is gels, okay? So gels also, they are industrially very important, as what I also showed the example, and it has very similar features of what I told before, but here you have a water or a solvent, and the chain has charge, and you want to calculate the mobility. So in this case, it's dependent on the number of free ions. And if you plot in the linear response regime, the diffusivity mobility, you can see the scale. But opposite to simple electrolytes, where if you increase the concentration, that mobility decreases. In these polymers, when you make them more and more dense, which is the number of monomers per cross links, then they actually increase. And this is because, again, when you put the field, why? Because they are condensed, they're tight along the chains, the counter ions, so there are fewer in this case. And when you condense it, they are free because they are very close and they can move around. So that's why they have this inverted thing, which is very similar to the other case. You still have the conformations change when you put the field. So this relation of how the mobility scales with a number of chains inverts here, and then you have this nonlinear regime. So I'm not saying that this is related to nonlinear conductivities, because we're not calculating conductivities, but it might be just some interesting systems to actually explore for applications. And this is where my work with Edwards goes. So now I'm going back to when I was a graduate student. So at that time, there was still the human genome didn't exist, but the second Nobel Prize of Sanger was on sequencing DNA. So you needed to make very short sequences that all in boxes that finish at the same amino acid and run them in a gel, and then you could read them back, by electrophoresis. And so this is what I did with Sam in a PhD. He didn't want me to do this. He wanted me to do two very strongly interfusing polymers with each other. So I had to modify the raptation to see how this force was going to distort the model of raptation of the gene. And the gene actually had the model of a fixed obstacles, but there were no computers. So what I had to do is I had to run to the Medical Research Center to use the machines there to do this simulation. And then I met people that told me about this problem. And I was very happy because, of course, the paper came in 86, but even in 88 and 89 is where the Human Genome Initiative came. And one wanted to know why the chains do not separate when they are very long. So, there was a lot of error to read the DNA. You have to cut it and so on. And they don't separate because when you have long chains, the long ones, they all move at the same rate. In the raptation model, the dynamics of the gene, he knew the chains are Gaussian and they have to move following a path that are Gaussian, and that the mobilities, the diffusion coefficient is 1 over n squared, the molecular weight or length of the chains. And so the mobility, which is the total force by this diffusivity, has to be 1 over n. Nevertheless, they couldn't separate long ones because the reality is that when they are very long and entangled, they don't raptate anymore. The fields are so strong that they can leak through the center. So the gene knew this model because he knew by an equilibrium, the steady state conformation of the chains would be Gaussian, but not anymore when you have a field. So that was what I did with Sir Sam. And I'm going back to this just to show that, today I continue studying these things, but instead of, I'm trying to do other techniques. How do you actually segregate or be able to change the mobility dependence? You have to get an n-dependence mobility to go back and separate chains. And this can work by confinement. Okay, so if you confine, say, in a tube, and you have charges, it's not very concentrated in charges, you have now the electron heterogeneities, and you can play with these parameters to see how, separate the chains according to size. And these models, here, if you plot the mobility of the chains over the size with 0, you have to have a surface charge in order to work. And it also depends on the size of the ion. So it's very related to the initial problem where in the mobility, if the ions are very small, then you cancel the charge, they condense very strongly on the chain, and so they don't move very large. But if they are larger, they are more free and you can separate. And this is the mobility of the counter ions, which is in the opposite direction. So, in a sense, that's why it shows this, and to introduce what I want to talk about now, which is these microfluidics with patches of charge and so on in the following. But I didn't know what Diderot was going to talk about, and so he has these papers where he's using this nonlinear conductivity, and I said, I'm not calculating the conductivity before, just the mobility, but it is based on the fact that you have to have non-ohmic behavior, okay? So you have to have nonlinear effects to be able to have a hysteresis and play with it. And so, he has very beautiful theories about the interaction when you have a strong confinement. If you remember your classes of image charge, you're pushing charges, the image charge is of, in a low dielectric, is of the same sign. So you are actually, they are interacting very strongly, almost logarithmic, like if it was 2D. And they depend on this parameter that in water can be significant because in confined water, the dielectric constant is not anymore 80, but it's much more reduced. It can be actually 7 or 5, okay? So in here, his parameter is that one that I introduced, 1 over gamma. Is the T star, which is kind of the inverse of the one of LB, or over some H is the separation between the systems. So I just thought it was nice to see the relations. So you have many regimes where you go below, as I said, around 0.1 in the polymers, you are in what is called the Jerome chains, where instead of just forming pairs, you start forming really long chains that correlate the system. And so playing with the time scales that have different phosphation dissociation, you can actually create very interesting devices. And I'm of course not going to talk about it in front of the person who did the paper. So anyway, well, maybe we do have in common that we're both very ambitious. So anyway, the point is I actually had been trying to work in these problems for a long time also, very obsessively on this charge system. So how do you deal with electric mismatch? And for the flat case of very large colloids, I had the student of René Van Rooij working in my group, and I had met Marcelja and Kallinger that had worked in this anharmonic HNC where, in order to calculate the image that you have when you are in confinement, they have a technique where they actually make a polydisperse in charge, a parallel, so it's only one dimensional. And we try to do this. And you can see that there are many effects when you have confinement. One is the size, the dielectric mismatch that pushes the charges away. And the other thing is the pressure that tries to pull them towards the walls. So if you have the dielectric constant of water, in a 101 electrolyte, you do have some absorption still. But in the higher 2-to-1 and 3-to-1, you have a depletion of them due to this image charge repulsive from the interface. So these things are very beautiful. This is just a simple example, not as complicated of the calculations you did, but to calculate the conductor, the electric in graphene, if you have, the people must remember this, if you have a conductor and you have a charge, the image charge is of the opposite sign. So it's a screen very strongly. So if you have these interactions between these two, if you look at from the top, it's like a gas, okay? Instead, if you are the electric, which is at the work of Didier and his group, is that because the image charge is the opposite of the same sign, basically these ions are acting if they have much more charge. Because, these image charges interact with each other, but the image charges, they don't interact with themselves. So basically, you are actually making like very strong valence ions. Okay, in the confinement. This one will decay, and probably if you were very strong confinement, will be just not even 1 over R, will be like quadrupole, okay, interaction. So this is a nice, film to show from the top. This is the gas phase, and then the electric, they are very correlated and form chains and so on. So I guess I just have to say here that with implicit water, these problems are very complicated. And you can imagine, you have to see also this response of the surface to the water, etc. And we have been working in code, so just in the case of non-explicit water. And so this is just to publicize that you can actually, we're going to download one more now that has more information. But to summarize, if you put the electric constant of the confined water like 5, you have, for the conducting, you have absorbed the charges to the interface, the electric or non-polarized in here away from the interface. And the electric field changes the conformation, as I showed before in the case of polymers, like here with zero field, you have the electric, and this is the conductor, and then you have the field, it reduces strongly. You calculate the conductivity, the current, and for the 3 cases, and also the conductivity. And you can see that in both cases, you can have different regimes, non-polarizable, polarizable, but the conductor very quickly stabilized to ohmic behavior, and the electric seems to be longer range. So all of the conclusions in his paper are very nice. So I just wanted to say that the things that are missing is precisely what he was talking about. How do you put, suppose that now you have corrugation. So when you put a field, you have to calculate the response of the surface to the electric fields, and adds another polarizability. So it's a much more complicated case. And this is something we're working on. You have to get the level of the electric tensor to calculate that. The parts I'm working on now is in electrokinetic flow, which is for hydrodynamics, and these are not anymore at the nanoscale, but more like 100 nanometers. So I'm interested not in externally induce these motions of charge, but induced by a surface that can have a gradient or can generate chemical activity and structural activities like the charge distribution that I saw in the beginning. So there is many groups that have worked on it. Generally, you will need an external field or something when you put a pattern to generate this velocity of the fluid. I'm not calculating conductivity. I'm just calculating the transfer of the fluid, okay? So there are ways to pattern these things. You can pattern, you can put electrodes and change the charge, plus, minus, and so on, and put them together and switch them. And so you can make those patches. You can also do micro pumps of activity, So in principle, they can be made. And this will be basically the structure that you have the system that can have positive and negative charges and places where you pump activity or when you suck in, okay? This will be the most general case, of course. And so the question is will such surface pattern induce the fluid flow? And how will it be on the unidirectional? And what is the average osmotic velocity depending on the parameters? So you have the fluxes and the charge densities. And so the student that is doing all the analytics is Ahis and the numerics, and he's working with another applied mathematician to get analytic results. But here is we're analyzing just the very long wavelength modes. So suppose these are the flux positive with some magnitude, and it has a cosine wave here. And then you have to get out of phase or alpha modified for the negative, or in general, you could have any values. And for the charge density, we assume it is also oscillating like that. So these magnitudes can be expanded to small magnitudes and do some approximations. But first, you get to see try to analyze what happened when you change these alpha and betas. I'm going to call the wavelength one of these k lambda, and it's from 1 nanometers, 10 nanometers. You can select values of k. No, this is actually, sorry, lambda here is the inverse kappa screening. So there are too many length scales. And this is the screening length kappa. So this is the radius of the capillary set of 100 nanometers and up. So I'm ignoring all of these polarizability effects. And this L is the inverse of the wavelength. And that's of the order of 1 micron to 10. Yes, that didn't match. Anyway, so we're just calculating the Poisson equation with the transport in the steady state without the time dependence, without convection, the flux, and an average Stokes without also just for the Stokesian flow, okay? And you have the boundary conditions of, the charge and the surface and the flow in the different parts. And so you can calculate this in the dimensionless space and make a perturbation with the boundary conditions. So everything, the perturbation is going to be the magnitude in these units of the fluxes and the charge, positive and negative. So when you do the analytic expression, just to understand what is happening, you have two terms, one that is only a function of R, and another one that can be positive or negative, that is a function of Z, okay, so an R. So the perturbation is quasi nonlinear because there are cross terms, of the order of the expansion that I told in the beginning. So this is what happened in the results. So if you have the fluxes and the diffusivity is the same in magnitude, then, and you have, say, alpha pi over 2 and beta 0, it means that the flux of the positive ions and the charge are on phase, but this one is out of phase. Then you generate actually the velocity in the system. No external field, right? So if you do it in COMSOL, you get very similar results to the analytics. Then if you actually put also a beta out of phase, all of them, you just get vortices. I mean, these are really, it's a cylindrical morphology, so they are really toroids around this. So there is no velocity in this case. And again, this is the COMSOL result. If you have, on the other hand, the negative with the positives on phase, and the diffusivities are still the same and the magnitudes, then you get a combination of the modes. This is very interesting because this is very similar, but it oscillates if you have a traveling wave with certain frequency of charge and in a system without a field. And it also generates directional modes of mobility. Anyway, so, and so this is the reason why when you put them together, this is the one that gives you mostly a directional flow. But when it's negative, you get the C dependence that can actually generate these vortices that you see that form in the system. So you can actually average the velocity in one of the wavelengths and calculate this velocity. And that depends, you can see that it will depend on the magnitudes of these G plus and G minus, that in the case that they are equal, and equal diffusivity, you could only get a finite velocity if you are out of phase, if your values of the beta is non-zero, right? Depending on the beta. And but if you have different diffusivities, then you can actually all the time get this non-average velocity. And so this is what, I mean, I'm just going to show that this is just to follow different values of this phase diagram. But what I wanted to show is what happened when you actually have different values of the mobility. And what happened in this case, if the positive, say, is less than the negative, then the velocity is in this direction. But you can actually reverse the velocity if you invert the actual value of the diffusivities between them. So, I like this idea that you can actually switch the direction depending on the flows, on the ion sizes and the diffusivities. And this is the case of, again, for the other values of alpha and beta, you get, in this case, just the vortices, but with some component. And here without depending on the value. So it's not symmetric. And then, you can invert the ion diffusivity ratio and get the velocities and reversal stage with this, playing with this out of phase where you have the fluxes and so on. So this is a summary of this part, and I wanted to show another part, but so I'm going to summarize very quickly. But basically, you get these gradients in ion concentration, electric potential, which induce this osmotic flow, and we can obtain a steady flow and average velocities in the capillarity when it's patterned by these and fluxes inside, and the mode can induce these circulatory and unidirectional effects. There are discrepancies in the type of fluidity you get, depending whether you have, you can switch the ions to show the direction. And so hopefully it will be applicable to some things. The other case I wanted to study was the case of a nanoscale patterning of charge, which many of you are probably familiar with cell diffusion phoresis, that you have to get a patch of a material that generates chemicals on one side. And so that moves, well, depending whether they absorb or not to the surface. And so there's also flux ionic species when this releasing flux has charges plus or minus. So this is similar to the other case, but why do I care about this? For a long time, I had been working in bacteria microcompartments, which are nanoscale, 40 to 200 nanometers size shells that are made up to, like, in the case of this PDU microcompartment, you have like 7 shell proteins, all different, and they have different charges between them of the components, and they have different interactions. So we know that they don't form icosahedra. When they are icosahedra, you could see that they have patches of charge in the surface. And these materials are actually concentrating. The function is that they concentrate. Here they concentrate enzymes. So bacteria, to survive, has these like nanoreactors, right? So they have enzymes inside, and so they have the surface, some proteins that absorb the reactant, and then some other part of the shells gets it in, they diffuse around, and they get in, and then they have a function, and some other part release them. So for a long time, I was just interested in why they actually have these patterns. And I think that they can actually have more function. I hope I'll show you now that they can actually move. They have been shown to chemotags if you put the product, but I'm going to show you they can do self-ionic diffusion phoresis where they have charges. So this is an interesting thing. I've been working for a long time because a buckling of things that have many components is not necessarily into an icosahedra. Okay, it can generate very complex polyhedra. So these are the shapes. So let's just go back to the simple assumption. This is what is known, and people had a story that is homogeneous charge, and you have flux on a Janus part. And here is the case of where you will have homogeneous flux and just charge on one side. So is it possible that these ones move? Of course, you can try to move more patches and do it in general. Okay. So the question is whether this case will also have direct propulsion. So here is we have a negatively charged system, and you can actually have a theta dependence on the surface of the charge, and consider the case of homogeneous or not. You have different diffusivity for the plus and minus ions that are released from the material. And so we're going to assume there is a dilute solution, and then you have a certain production of the ions I. In this case, it's not J, it's I. And you have make mean field approximation. Again, you can have the concentration and the velocities, and you have to find the potential along the surface. You can show, in the time scales or the systems that you are in regimes where you have low Pellet number, and also low Reynolds number. So when you calculate the dissipation to the driving part, and the parameters for these sizes, you are very much in the regime that I talked before, the Poisson equation with the ion transport in this limit, and also the Navier-Stokes in the compressible low Reynolds number. So now you put a simple parameter to describe the charge, and you have all the boundary conditions at the surface and the fluxes, at the interface, and you have the velocity will be UZ in this case, represented by U. And in the bulk far away, you are going to assume just at infinity, you have a constant concentration of charges that doesn't change with time, right? And you have also the passive and active parts, and the passive parts in equilibrium far away is just the Poisson-Boltzmann, and then in the surface you get this. You can do an expansion again, and what allow you the expansion is to get an analytic equation, and this analytic equation in the Toledo order is just a function that depends the coefficient of the different diffusivities, and the function that in the limit of very small will just go to this coefficient value, 48. R is the size of the particle, and the very large limit, it will not move velocity. So this is the plots. This is plotted versus Q star, which is the limit of the analytic value that you can have with respect to that one. And you can see, how the flux will be as a function of the different parameters of the Q over the maximum value of analytic results when you start moving them. And it's pretty good agreement with the COMSOL too. The interesting thing is like the potential is very asymmetric around the particles. And, this is like a near field around where there has a gradient of the charges. You can have actually the effect of asymmetry that causes the mobility in this direction for the particles. So because you can have different diffusivity of the positives, and then you have also the flux that is changing the concentrations from right to left. And so just here to compare how can you enhance the mobility of the system? So you have the case 1, which is the one that has been studied. The case 2 is that when you have homogeneous the flux, but you segregate the charge. And then the case 3, which both of them are separate. So suppose it's true that this microcompartment has some parts that absorb and some other ones that are charged and so on. Then, we tried this one just in that limit of where you can do it analytically, and it's actually showing to be the larger mobility, which is this number 3. The other ones, these two are similar, and this is the worst, to have the charge patterns. It's the same place where you have the ions move. So this is this is a silly film because it's a static and you're just showing COMSOL how they're moving. So I am going to summarize that you have a surface charge asymmetry provides an alternative mechanism for which you can have ionic gradients. We have to be careful again here I have not assumed that they can rotate, okay? So if you have the rotational degrees of freedom are too large, which they won't have really a high velocity for a long time. And when the particle size number is comparable, the mean field hydrodynamics play a key role. And the Janus endow both surface charge and ion symmetric results to enhance propulsion seats. So we have shown this is another way of fluoretic self ionic mobility, diffusivity, propulsion, sorry. I just was wondering now to when can you push these? Of course, you cannot think of enzymes can actually propel, but, because it will depend on the size and this rotational degrees of freedom. So I hope that these shapes that are so asymmetric inhibits the rotation. It's very hard to have self-propulsion for long. Yes, so I mean, when we try to design macrocompartments like that and with magnetic particles and superparamagnetic, you have to compensate torques to return to the direction of the flow and so on. So anyway, I don't know if I'm on time or too early or too late, Jasna, but
You did great.
Thank
so
you.
You have exactly.
So thank you very much. This is Nicholas.
Thank you, Monica, for a lovely talk. Questions? Go ahead.
Very nice talk, thank you. You had several occasions where you have a flux in or out of the surface.
Yeah.
What sort of physical mechanism do you have in mind? Electrochemistry or decarbonation?
Well, you can decompose the material, like I saw the urea and so on, that you can have, but that they're going in, you let them push in, or something that is absorbed, I don't know how to, I just wanted to do the general case because I wanted to do these ion pumps that can come in and out and change the flux. I want to see whether it's possible, if you have something of charge that is, patchy charges, you can generate it. But yeah, it's going to be more difficult to come down. You can do only one. And also, it's nice to have both because then you can average nicely over one amplitude, both. If you have only one coming out, you can do it in COMSOL, but it's much more difficult to get the analytics working. This is what we're trying to do. You can do two in COMSOL. We have been doing the chemotaxis when they are true and they are consuming and they are also inhibiting because they have bulkiness that they take the material. You could do it here with 2 in COMSOL. If you want to do more than 2, you have to do Stokesian dynamics, and then it will be much harder to put other shapes or other patches and so on. Yeah. It's possible to put mixtures of sizes in Stokesian and so on, but it's much harder then. Yeah, they interact. I mean, basically, that's what I was trying to look into, whether there is cooperativity, but I don't think we're going to be able to do it for these very complex shapes. Yeah, maybe in the chemotaxi with consumption. Yeah.
So,
They are solved self-consistently, all the equations. Yeah, there's people that actually put, the hydrodynamics separate and they put molecular dynamics. No, these are just all in continuum, solved self-consistently. Oh, that vector number is very low, yes, in that, yeah. But you are taking into account the particles that are released, and so on. Yeah. I'm assuming in these calculations that it's really infinite. You have a problem at the surface. I mean, you yourself couldn't solve very well what happened to the field and so on. So, yeah, we are assuming it's an infinite system. You can do in COMSOL some effects on the surface, and yeah, it's yeah. You're going to talk about it tomorrow, a bit. It is, yeah. I know. So, yeah. I would be what I want to do is that, yes, and put them in series, or how does you modify and the flows.
okay, if there's no further questions, let's thank both Liedrich and Monica for the